Hi friends, this is Narasimha, studying BTech first year of CST group in IRE College. Today, as a part of my AIT Tech Talk videos in the subject of applied physics, I want to explain about a topic named specific heat. We all come across this topic in our secondary school education, means in the 10th class or in intermediate or in BTech level, and so on. It is a thermodynamic topic. Let's get into the topic. Specific heat. The specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. The relationship between heat and temperature change is usually expressed in the form shown below, where C is the specific heat. The relationship does not apply if a phase change is encountered because the heat added or removed during a phase change does not change the temperature. In these three paragraphs, we have come across a definition of the specific heat and the relationship between heat and temperature and the relationship between the change in the temperature. Next, coming to the formula of specific heat. While we are solving problems related to heat functions or the specific heat, we need a formula to solve the complex functions into a simple solutions. And the formula for a specific heat is Q is equals to C into M into delta T. Q represents the heat added and the C represents the specific heat, M represents the mass and delta T represents the change in temperature. And delta T is commonly known as T2 minus T1, where T2 is the last temperature and T1 is the primary temperature. The specific heat of water is 1 calorie per gram degree Celsius, which is equals to 4.186 joule per gram degree Celsius. This is the 1 calorie is equals, and this is usually known as 1 calorie is equals to 0.186 joules, which is higher than any other common substance. As a result, water plays a very important role in temperature regulation. The specific heat per gram for water is much higher than that for a metal, as described in the water metal example. For most purposes, it is more meaningful to compare the molar specific heats of substances. In the para, we are getting to know that water is much higher than for the metal in the degrees of specific heat per gram. The molar specific heats of most solids at room temperature and above are nearly constant in agreement with the law of Dulin and Petit. At lower temperatures, the specific heat drop as quantum processes become significant. The low temperature behavior is described by the Einstein-Debye model of specific heat. Coming to specific heat of solids. The specific heat of copper is 0.093 calorie per gram Kelvin, which is also converted as 0.389 joule per gram Kelvin, and that of lead is only 0.031 calorie per gram Kelvin. This is also converted as 0.13 joules per gram Kelvin. Here we come across the copper and lead specific heat values. And next paragraph. The difference is mainly because it is expressed as the energy per unit mass. If you express it as energy per mole, they are very similar. It is in fact that similarity of the molar specific heats of metals which is the subject of the law of Dulin and Petit. The similarity can be accounted by applying equipartition of energy to the atoms of the solids. Coming to specific heat of gases. The specific heat of gases are generally expressed as molar specific heats. For a monoatomic ideal gas, the internal energy is all in the form of kinetic energy, and the kinetic theory provides the expression for the energy related to the kinetic temperature. The expression for the internal temperature is shown below. That is U is equals to small n into Na into Ke average. That is equals to small n into Na. Here Na represents the Avogadro number and 3 by 2 into Kt, which is also simply known as 3 by 2 into N into R into T. Further application of the ideal gas law And first law gives the relationship as Cp is equal to Cv plus R. The ratio of the specific heats V is equal to Cp by Cv. The R is equal to Cp by Cv is a factor in adiabatic engine process and determining the speed of the sound in the gas. This ratio V is equal to 1.66 for an ideal monoatomic gas and V is equal to 1.4 for air, which is predominantly a diatomic gas. The values which I have mentioned here, V is equal to 1.66 and V is equal to 1.4 are very useful while you are solving the problems. Please remember guys. Next, coming to units of specific heat. For any term, there are units to express. For specific heat, units are very important for expressing any thermodynamic property which I have said before. The same is true for specific heat. Energy is in the form of heat is expressed in joules or kilojoules. Joules are shortly denoted by small j and kilojoules are shortly denoted by kj, which are most common units associated with energy. One unit of mass is measured in grams or kilograms with regard to specific heat. Per 1 gram is the standard form used in tables of specific heat values, but references using 1 kilogram are sometimes seen. The standard values I will show after this slide. Next, coming to factors that determine specific heat. For any thermodynamic property, some factors will oppose or some factors will accept to increase the nature of the property. Coming to specific heat, the temperature and pressure play a crucial role in determination of it. Two factors that change the specific heat of a material are pressure and temperature. Specific heat is defined as the standard constant pressure, usually atmospheric pressure, shortly known as ATM, for materials and is generally reported as 25 degrees Celsius, while in conversion we will use as 298.15 Kelvin. A standard temperature is used because specific heat has temperature dependence and can change at different temperature values, which I have mentioned before. Specific heat is referred to as an intensive property. Next, coming to another factor, energetic degrees of freedom. A large factor in the magnitude of the specific heat of a material lies at a molecular level in the energetic in degrees of freedom. Degrees of freedom are available to the material in the phase, solid, which may be solid or a liquid or a gas, in which it is found. Energetic degrees of freedom are of four types. They are translation, rotation, vibration, and electronic. A minimum amount of energy is needed to reach each degree of freedom. Next, I want to show a picture by which you can understand for what purpose the specific heat concept is used in our day-to-day life. Here you can see one pan and one pot, and it is an iron frying pan and another one is earthen pot. In the first case, the water will be easily warm up because the specific heat is smaller. And in the second case, the specific heat is greater, so it will take more time to warm up. Please have a look to this diagram, friends. This diagram says about the use of specific heat in our day-to-day life in warming water. It's an example just. Next, the specific heats and molar heat capacities for various substances at 20 degrees Celsius. Now, I have mentioned before that while solving the problems, we have to get into the problems and we have to use the specific heats of the materials. And here are some of the substances and degree Celsius in joule per gram Kelvin, and C in calorie per gram Kelvin or BTU for LB for heat, and molar specific heat, which is in units of joule per molecular Kelvin. And here are some substances such as aluminum, bismuth, copper, brass, gold, lead, silver, tungsten, and etc. which you will come across while solving problems. While solving problems, we have to use these values for getting an approximate solution. And thank you friends. I hope my lecture is useful for your further studies, and thanks for watching.